Okay, let's look at lab 9, part 2. This is a current to voltage amplifier. This is kind of cool because it's going to turn out that many real-life sensors, so for example like a real-life photo sensor, will behave kind of like a weak current source. So often, a sensor will produce a current in response to some incoming signal. This is especially true of things that detect photons. But it's not a great current source. It's actually kind of it's a current source that um, it prefers the easiest possible load. And remember, the easiest possible load for a current source is a short circuit, just as the easiest possible load for a voltage source is an open. It's where it's a very large resistance. Right, and this is another way to think about that is when you want to measure a current without disturbing it, you use a current meter that has a very small internal resistance, ideally 0. When you want to measure a voltage without disturbing it, you use a voltmeter that has a very large internal resistance, ideally infinite. Or with our handheld voltmeters, it's 10 mega ohms. So this isn't so much real life, but this is our example. We're going to analyze it first. So here is a 1 microamp current source. It's actually a current sink because it's bringing current down. So like something that outputs current is called a current source, and something that kind of inputs current and brings it down to ground is formally called a current sink. Anyway, so we have a 1 microamp current sink. So this current is going to the left here. So we have this current kind of going to the left and down into the current source. And because the op-amp input draws no current, that current has no choice but to flow through this 1 mega ohm feedback resistor. So the same current I that flows to the left and down also flows to the left through this feedback resistor. Okay. So this I is the same as this I, and then we can say, using Kirchhoff's voltage law, or kind of using Ohm's law basically, we're going to say V out minus IR feedback equals 0. And that's basically using Ohm's law to say the voltage drop across this feedback resistor is this current I times our feedback. Right, if the current flows this way, then this point is higher than this point. So it's basically, you could call it KVL, you call it Ohm's law. And we're using the fact, again, that this point is a virtual ground. It's a virtual ground because we have, because the feedback, the negative feedback, is going to allow the golden rules to work. So first of all, the inputs draw negligible current, and as long as feedback is working properly, the output will do whatever it needs to do to ensure that these two inputs are the same voltage. So this is stuck at ground, so this becomes a virtual ground. This is a pretty common configuration where you ground the non-inverting input, and then the inverting input, as long as feedback is working, is a virtual ground. Okay, so that says that V out is this feedback resistance times I, which is 1 mega ohm times 1, in this case it's 1 microamp, so this is 1 volt. But basically, so we have this tiny current, microamps, and we're going to get, in response to that, an output that's a reasonable size, volts. Okay, that's pretty good. Now let's put it to practical use in kind of a fun way. We're going to use an infrared light-emitting diode to transmit some light, and then we're going to use an infrared photodiode to detect that light so that photodiode will behave like a weak current source. And remember, the easiest thing for a current source to drive is like a short circuit to ground, and this is basically a short circuit to virtual ground, so that's good. That'll be very easy for the current source. Since it's a weak current source, we want to make it easy. And so we'll amplify that received light signal and look at it. So let me just pause and redraw that. Okay, so we are using a 940 nanometer LED. So lambda is 940 nanometers, so if you put in the forward voltage of the LED when it's on, is going to be, the LED won't really emit any light unless the LED voltage is at least as large as Planck's constant times the speed of light divided by the charge on a proton and then divided by lambda, so hc over E lambda, so it's about 1.3 volts. So then what you see, so here we have an arbitrary waveform generator. So we're going to send, some kind of a signal from the waveform generator through here, and out here. So then it's going to flow through the resistor and then down through the infrared LED. So this current flowing down through the LED is basically going to be this input voltage minus the LED forward voltage divided by this resistance, 100 ohms. That's as long as it's big enough to turn on the LED. And if it's not, then we'll get no current, because you're not going to get current flowing backwards through the LED. And also, you basically get negligible current if this voltage isn't big enough to turn the LED on. And it's so small but negligible. So, okay, so we will, and then I guess I didn't try to work out approximate numbers, but if this is, let's say it's like 2 volts, and then 2 volts divided by a kilo ohm would be 2 milliamps. So I guess it's going to be about 20 milliamps. We're going to get about 20 milliamps through this infrared LED, and it's going to sort of be time varying because it depends how far above this LED forward turn-on voltage, like the diode drop for the LED Vin actually is. Okay, so we'll have this periodically varying current through the LED. That's going to cause a proportional flow of infrared photons out of the LED. And then some small fraction of those photons will strike this photodiode. So then we'll have a current flowing down through this photodiode here, which is proportional to the current flowing through the LED. It'll be probably much smaller, but still proportional. And then again, so now we use our current to voltage amplifier that we just described a moment ago. So we get this output voltage, which is proportional to this detected current. This output voltage is proportional to this detected current. And this detected current is proportional to this this output voltage is proportional to the current through the photodiode, which is proportional to the light detected by the photodiode, and that light detected by the photodiode is proportional to this light emitted by the LED, and the light emitted by the LED is proportional to this current that flows down through the LED. And then remember, we have, so pin 3 of the op-amp is the non-inverting input. It's connected to ground. Pin 2 of the op-amp is the inverting input, so it's connected to the output through the feedback resistor, and it's connected to through this infrared photodiode to ground. And then pin 6 is the output of the op-amp, so it goes through this feedback resistor back to the inverting input. That gives us negative feedback. And then you always have to remember to connect the power. So we have the positive supply voltage up is pin 7, that goes up to plus 9 volts, and the negative supply voltage is pin 4, that goes down to minus 9 volts, because plus or minus 9 is the most that the EE board will give us. And then, okay, good. And we have our little diagram of what's where on the chip. So 1 is a no connect. Here's 2 is the inverting input, 3 is the non-inverting input, 4 is negative power, 5 is a no connect, 6 is our output. And we always have some kind of negative feedback from the output back to the inverting input, and then 7 is our positive power, and 8 is going to be a no connect. Okay, so I have that wired up, so let's see what that looks like wired up. Okay, so you see I have here the op-amp, and then here's the 1 mega ohm feedback resistor from the output back to the inverting input. I have this scope probe. Channel 1, the yellow scope probe channel, is observing the output of the op-amp. Here, this red wire is my power connection up to plus 9 volts. This red wire is my power connection down to minus 9 volts. This black wire is the non-inverting input being grounded. And then I have the infrared, the photodiode. The infrared photodiode is this black object down here, and it's bent over so that its top, because the sensitive part is the top, so its sensitive part is pointing toward the infrared light emitting diode. So let's see, the short lead coming out of it is grounded, the long lead coming out of it goes into pin 2 here, the inverting input of the op-amp. Now, oh, by the way, I guess I could see this. This tiny little red jumper wire is how I distribute the negative power to this red bus on the bottom, and then this black wire here is how I distribute, I connect ground to this blue bus on the bottom, and then this red kind of 10 centimeter long wire is how I distribute the positive voltage, the plus 9 volts, up to this red bus on the top. So that keeps my power nice and neat. Then, here is my arbitrary waveform generator. I used a blue wire for that. My arbitrary waveform generator is going to the left end of this 100 ohm resistor. So this is a 100 ohm resistor. I have scope channel 2 observing what's coming out of the AWG. So it's going into the top of that resistor. That's the blue or cyan scope channel. And then I have okay, so then here's the resistor. At the right-hand side of that resistor, I have this infrared LED. So the long end is plugged into the right end of the resistor, and the short end is plugged into ground here. And it's connected so that the little lens is looking to the right. So the little lens is where the light comes out of, so it's pointing toward the photodiode. And then I have scope channel 3 looking at the top of that infrared LED, just so we can able to see what the diode drop is. Because we estimated it should be 1.3 volts roughly when it's on, so we can see how true that is. Okay, then I guess the proof that this thing works, so with all my dark backgrounds, I have some black construction paper here. So you can see on the top right corner my waveforms. So you can see the yellow waveform is what's coming out of the op-amp. And if I put my little black piece of construction paper in between, then the output of the op-amp disappears. And then I can remove the piece of construction paper and the output of the op-amp reappears. So that's really cool. You get this very dramatic disappearance and reappearance of the signal just by blocking the light with a piece of black construction paper. Now, let me give you a close-up of the waveforms so you can kind of look more closely and see the scales of things. Okay, so if you look at the cyan or blue scope trace, then that's what's coming out of the waveform generator. So I have a 5-volt offset and a 4-volt peak-to-peak signal, so it's going back and forth between 3 volts and 7 volts. So it's going from, so it goes, there's 5 volts minus 2 up to 5 volts plus 2. So it's going back and forth between 3 volts and 7 volts. And then on a much magnified scale, scope channel 3, scope channel 3 on a much magnified scale is, you can see that I have the top of that infrared LED is going between about 1.2 volts and 1.3 volts. Okay, so I guess it's like going from kind of just barely on to quite fully on. And then, so maybe, that's interesting, I calculated 1.3 volts, but this is only sometimes about 1.2 volts. Okay, and then we can see with channel 1 of the waveform display, so it's on another different scale, different offset. Why is it negative? That's actually interesting that it came out negative. I don't understand why it's negative. It should be positive. Gee, okay, that's kind of a mystery to me that it's negative. Huh. I don't know. I wonder if I have the LED upside down. I mean not the LED. Sorry, I wonder if I have the photodiode upside down. Anyway, okay. In any case, it's the sign is a mystery to me, but here we have -4 volts, there's -2 volts, -6 volts, so pretty big amplitude, right? So this amplitude is like about 4 volts peak to peak. And I can use like a not quite so opaque piece of, here's like a piece of old cut up white t-shirt. So if I can block a little bit less of the light there, and you see, yeah, the signal gets smaller, but it's still there. And so it kind of blocks just a little bit. Another thing I can do, another thing I can do is if I just move the infrared photodiode a little bit so it points, see, because here's my infrared LED transmitting light, here's my infrared photodiode receiving that light. So if I just reorient this thing a little bit, so you see if I make it like a much more directly aimed, because the guidelines ask for about 10 centimeters and I think I've only got about 5 centimeters here. So you see I'm really kind of overloading it. I guess I'm kind of reaching the power supply limit there. Or if I kind of tilt it away a little bit, then I get a smaller amplitude. So that's kind of cool. So you can kind of, seems quite plausible that the amplitude of this signal depends on what fraction of the light emitted by that LED is actually captured by this photodiode. So that's pretty cool. I don't know. I think the whole thing is pretty cool. Okay, so that was Lab 9, Part 2, the current to voltage amplifier. Again, I think that's pretty neat. So you get to transmit something through empty space with invisible infrared light, and you get to see how you can detect a weak light signal using the IR photodiode. Okay, before I go, one more little trick. So I actually just reversed the direction of that photodiode. So I flipped it around so that the long end and the short end were swapped. So basically, I guess it's like turning the diode upside down in the circuit diagram. And now you see, if you look at the waveforms, that the signal coming out of the op-amp is positive instead of negative. So I just swapped the direction of the current, and now I get a positive signal instead of a negative signal out of the op-amp. So now the current must be flowing down to ground through the photodiode, whereas initially the current was flowing, I guess, up into the op-amp. Okay, so that's kind of cool. And now I think we're done.